The broadcast is now starting. All attendees are in listen-only mode.
Hey everybody, welcome back to Young Engineers of Today. Hope you're ready to continue with Fly to Learn because that's definitely what we're going to be doing. And like I was saying to the middle school class, excuse me, like I was saying to the middle class, uh, yeah, I'm not going to go there. Um, this is probably what we're going to do to finish out the semester as well, just based on the trajectory that we seem to be heading in. It kind of looks like we'll be doing Fly to Learn until the last class, because typically the last class is a class that we spend sort of talking about the future, you know, the engineering colleges and what you can do with an engineering degree and things like that. So, um, based on sort of where we are in the year and how much Fly to Learn we have left, that is my guess. Historically, hasn't always worked out that way. Sometimes, there's like a class or two left over that we spend doing sort of one-off things. So it's possible that we'll run into a situation where we don't have uh, like a whole bunch of stuff to do. Um, but that is my guess for the rest of the semester. If you really like Fly to Learn, perhaps this is good news. If you're not a huge fan, well, I apologize, but we'll spend some time working through um, working through Fly to Learn, and then we'll round out the year with a nice discussion. And anyway, it should be pretty interesting. So today we're going to get started on power loading. Now, those of you who weren't here on Monday, I apologize, but as I understand it, there is no recording for Monday's class. So I don't think you missed much, though. As I as I heard, I guess you guys went pretty much over wing loading, including all the testing and everything like that. So you probably didn't really have to worry about um, you don't really have to worry about missing anything. Anyway, power loading is the next logical step after wing loading. Power loading is the ratio of horsepower to weight. Horsepower is a measure of power. An engine creates horsepower by changing the potential energy of fuel into the kinetic energy of turning pistons. If you're not entirely sure how an engine works, I have this convenient diagram here that I drew from my middle school class. So basically, you've got pistons inside of a tube, or the piston shaft, um, that have an air fuel mixture pumped in. These pistons are all either in a line or a V or something like that, which you might hear, an inline six or a V8. Um, if it's a V style design, that's because the pistons, if we were looking at it from the front, alternate, either pointing to the right or to the left as you go backwards. So like this might be piston one, this might be piston two, this might be piston one, this might be piston two. Anyway, inline, by comparison, all of your pistons are in the same line. Point being, your pistons are all hooked up to a crooked shaft, in essence, that is, by extension, hooked up to the propeller. Now, the shaft spins along a very specific axis, so like this propeller doesn't like wobble around everywhere. It'll just spin smoothly. But what happens here is, let's say, for instance, if this piston were to go down, it would cause the shaft to spin, which would cause this piston to go up. Now, as this air-fuel mixture is being pumped into here, the idea is to make that fuel in the air-fuel mixture explode, because it's explosive. That's why we use it. It's specifically because that stuff has the ability to blow up. And Well, there are a few different ways to make things explode. Uh, the end result is always heat, but um, you can cause air to become hot enough and fuel to become volatile enough by forcing it into a smaller and smaller area, because as you force it into a smaller and smaller area, the pressure increases. Pressure um, can be directly correlated to heat. So as the pressure increases, so does the heat. As the heat increases, eventually you reach a point where the fuel is energetic enough to ignite. So as this piston moves upwards, it compresses the air and fuel mixture more and more and more and more and more and more until it gets to a point where it's too much and it explodes. And what that does is that forces that piston downwards. Now, because it's hooked up to the same shaft as this piston, it causes the shaft to spin, which causes the shaft to spin over here, which forces this piston upwards. And the same process repeats over here. So then this piston starts heading up, 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 and then it hits the critical point, and then it explodes back downwards, and so on and so forth. And so each of these pistons will sort of swap position. Now, granted, that's a two-stroke engine. Planes are going to have more than just, or that's not a two-stroke, but it's you know it's a two-stroke is a different thing, but in this case it's an inline two. Planes are typically going to have more pistons than just two. A lot of planes are going to be running 6, 8, 12. If they're a propeller plane, because you want to generate a lot of horsepower, and planes tend to weigh a lot. Like not a bunch compared to a car necessarily, but it can depend. Planes can be larger, and the wings can create a fair amount of weight. And anyway, I'm getting ahead of myself. Point being, you want a fairly strong engine on a plane. So an engine creates horsepower by changing the potential energy of fuel, that is, the energy that could be of fuel, into the kinetic energy of turning pistons, that is, the energy of the pistons moving and causing the shaft to spin and making the propeller spin. The propeller acts like a wing to pull the plane forward as it spins, and then the plane flies and everybody's happy. The power of the engine is called brake horsepower. This is basically the raw power that an engine can create. So whenever you're referring to brake horsepower, that's just what it can do. Now the prop converts about 80% of this power, brake horsepower that is, into pulling the plane forward. That's because some of this energy is lost in translation. Sometimes it gets converted to heat, sometimes it gets converted to sound, sometimes it gets converted to whatever. The plane also isn't going to 100% be able to just, convert all of its brake horsepower into forward motion based on external factors. Sometimes the air is thinner, so it's it'll have a harder time. Whatever, you get the idea. But about 80% of the brake horsepower gets converted into pulling the plane forward. This amount is referred to as thrust horsepower. So thrust horsepower is strictly the amount of forward pulling power that the plane has. And this is in contrast to brake horsepower, which is as much power as the engine could possibly create, as much as it's physically possible for it to create. Then, if you run a plane at 100% power, the engine's going to wear out. The gas mileage is going to be bad, and generally your plane is not going to be running at peak efficiency. So for that reason, airplanes are typically run at about 75% max capacity. This 75% of thrust horsepower is referred to as cruise horsepower. So to summarize, you've got brake horsepower, which is its raw power. Then you've got thrust horsepower, which is the forward power of the plane after, sort of energy is lost in the conversion to forward motion. And then you've got cruise horsepower, which is the thrust horsepower, but not run it like 100% so that you don't burn out the engine. So cruise horsepower tends to be a fair amount of cruise horsepower tends to be a fair amount less than the brake horsepower. And there's a little bit of math required to determine it. So you may be thinking, well, you know, well, it takes 3 calculations to find out just how much power is needed to fly. And yeah, that's true. Engineering can require math, and it doesn't require complicated math necessarily, as you can see here. This is just multiplication or division. Multiplication by a less than 1 number, or division by a number greater than 1, whatever. You just need a solid foundation of math, though. Some of the math can get a little bit complex later on, but as it stands right now, this is all pretty straightforward. And if you're able to do this, then you've got a promising start in career designing and flying airplanes for test and making tons of money doing it. So, in essence, math is useful. So we're going to increase the horsepower of the plane in order to examine its impact on weight to power or power loading. Listed below are engines with different horsepower ratings, and what we're going to do is we're going to divide that horsepower by the gross weight in order to get the power loading. So for instance, I've got my calculator here. We've got 150 horsepower and 2,500 pounds. So 150 horsepower divided by 2,500 is 0.06. So yeah, 0.06. To continue with that, 200 horsepower divided by 2,500 pounds gives you 0.08. Continuing with that, 250 divided by 2,500 is 0.1. Why is it? Oh, whatever. Is that backwards then? Why is it 2,500 divided by 250 now? In the last class, it was 250 divided by 2,500. All right, so this might be backwards. I suppose that would make sense as well. So each single horsepower would need to move 16 pounds. All right, so this aligns more with wing loading. 2,500 divided by 200 is 12.5. Um, 2,500 divided by 300 is 8.3. 8.3. And finally, 2,500 divided by 350 is 7.1. So as you can see, as the horsepower increases, the power loading decreases. And the power loading decreasing means that there is more, basically the ratio of power to weight is better, because that means that, like with wing loading, as wing loading decreases, that translates to each square foot of wing has to lift less weights. As horsepower increases or weight decreases, each single foot-pound of horsepower must move less weight. So power loading decreases as horsepower increases, which is a good thing. Oh, that was interesting, calculator. Okay. Likewise, as we decrease weight, our power loading is going to likewise decrease. And as our power loading goes down, our plane becomes more efficient. So as gross weight increases, our power loading increases. Because 250 divided by, or excuse me, 2500 divided by 250 is, 10. I don't know why this is in the other direction now. 2250 divided by 250 is, oh geez, what is that? So 9. And that's 8 and 7 and 6. So yeah, the power loading will decrease. So as the gross weight decreases, does power loading increase or decrease? Our ratios don't stay the same here. Okay, so as gross weight increases, does power loading increase or decrease? So as the weight of the plane increases, does our power loading increase or decrease? We'll go by the first ratio up here, which is its weight divided by power. So if it's weight divided by power, which is going to be it's meant to be a bicep. So weight divided by power, if the weight is on top, and that goes up, that means that the overall value is going to increase. So our power loading will increase. But remember, that's not necessarily a good thing. We don't want it to increase. Our 275 horsepower plane has a gross takeoff weight of 2,500. What is its power to weight ratio? 2,500 divided by 275 gives us a power to weight ratio of 9.09 repeating. So 9.1. Say it's 9.1. Our small private plane carries 4 passengers. The plane weighs 2,400 pounds. The airplane's required brake horsepower is rated at 150 horsepower. What is the required thrust horsepower? How powerful must our engine be to fly at 75% thrust horsepower or cruise horsepower? So this has already pretty much been calculated for us, which is pretty straightforward. So if we've got our required brake horsepower is 150 horsepower. The thrust horsepower, if you remember, is roughly 80%. So if we take 150 and we multiply it by 0.8, we get 120. Cruise horsepower is 75% of thrust horsepower. So we multiply this again by 0.75, and we're given 90. So our cruise horsepower is 90. And that's just some simple sort of reductions and things like that. I have a power to weight ratio of 0.09 horsepower per pound. The plane weighs 2,600 pounds. What is the horsepower of the aircraft? This is a little bit messed up. This should be the other way around, but that's okay. So we'll just go ahead and skip that. So what we're going to do is we're going to mess around with plane construction now. So I've got my plane maker. I'm going to go ahead and open, don't save. I'm going to open that RV10 plane that we've been messing around with for every single custom plane construction. If it asks you to save, don't save. So now we've got our RV10 open, and then we're going to save 3 versions of the RV10, WP150, WP300, and WP600. So in this instance, we'll go ahead and go up to Save As, and we'll name it Thomas WP1, was it 150? Yeah, 150. Obviously, don't put Thomas there, put your first name. Save aircraft, then Save As, and instead of 150, we're going to save it as 300. and then save as one more time. And instead of 300, we're going to do 600. So what this should do, if we double check by clicking open, it should, oh, whoops. Why? There we go, save aircraft. It should have saved 3 separate aircrafts here. So let's go ahead and open up the 150. Look at that, that's our plane. Pretty basic, just like it was before. Makes sense. Now we're also going to apparently change the wing length. Okay. That's fair. We'll go ahead and do that. So let's start out with WP 150. WP 150 means we've got 150 horsepower. So if we go up to standard and engine specs, we've got maximum power of 260, which I suppose we'll put into here. So maximum power of 150 instead. So under prop engine specs, we're just going to change the maximum power to 150 horsepower for our first plane. We'll go ahead and close that out. Go to standard and then weight and balance. Our total weight should be 2,500. So let's see, our empty weight is 1,700 and our fuel load is 3,800, or excuse me, 380. So let's see here, we want it to be 2,500, which means that 2,500 minus 380 is 2,120. This is going to be 2,120. Perfect, so our empty weight is 2,120 and our fuel load is 380, which brings our plane weight up to 2,500, which means our weight to power ratio is going to be 16.67 because we've got 150 horsepower and weight of 2,500. We'll increase the maximum weight under the weight and balance to 3,000. So now we've got a maximum weight of 3,000. And then we'll go ahead and change the wings here. So if we go to standard and then wings, we want our wing 1 semi-length to be 15 even. So this is just like the wing loading that we did before. And then our wing 2 lat arm is going to be 14.95. 14.95. And our wing 2 vertical arm is going to be negative 0.35. And when that's done, our first plane is ready to go. So we can just go ahead and hit save, and it will update that WP 150 with the correct value. Now let's go ahead and do the same for the 300. Open aircraft, weight and balance. We're going to increase it to 2750. So 380, 2750 minus 380. 2370. Maximum weight is going to be 3,000, just like before. Then we can go under engine specs, set our maximum horsepower to be 300, which should give our weight to power of 9.16. And then we can go ahead and, under wings, adjust our wings appropriately. And as you can see, the wings are a little bit weird here. So we set it to 0.75. So we got some very short wings. And then 0.7.45 and negative 0.85. And this is our second plane. Is there a way to reset the wing length? I believe your best option is just to reopen the base plane model for this, or the base plane specs. So if you haven't saved this file, the WP whatever, since you created it, just go ahead and reopen it, and you should be able to reset the wing length back to what it was. And then finally, we're going to set up our 600. So if we set our engine specs to 600 horsepower, perfect. Let's set our weight and balance. So now we're going to 3,000 minus 380, right? Yeah. 2620. I really should have just done the math on that. 2620. All right, and the maximum weight is going to be 3,500. Perfect, and then we can go ahead and mess with the wings on this one as well. So it's going to have a semi-length of 30 feet. Going to have some long old wings. And then 29.95 and positive 0.55. And there is our final plane. And so once you've created all three, go ahead and open it up into X-plane and see how long, basically see how fast you can fly the plane. You want the true airspeed, which is going to be the last two checkboxes on line 3. So what I'm going to do is I'm going to go ahead and leave these instructions right here so that they're visible, and give you guys, give you guys, well, really as much time as you need. Once you're confident with this and you've flown it, you're going to fly 3 tests for each plane. You want to figure out the wing load, the aspect ratio, the power to weight ratio, and how fast it can fly. And this way we get a decent idea of how each of these planes differs. But yeah, once you've done your 3 test flights and you've noted how fast the plane takes off, 3 test flights per plane design, 3 test flights per plane design, and take note of how fast, true airspeed, how fast the plane is flying whenever it takes off. Establish and maintain level flight for 3 minutes. Okay, for level flight for 3 minutes, and see how fast the plane goes, and then we can move on from there. Once you've done that, though, go ahead and raise your hand, and I will have a pretty good idea of how close everybody is to finishing. How's everybody doing with the test? And just just a reminder, go ahead and raise your hand whenever you're done. Also, that's not meant to be a rush. I just wanted to make sure everybody remembered. We'll give everybody about 10 more minutes too, and then we'll start doing the poll questions and stuff like that, and wrapping up for the night. So again, no rush. If you don't finish the testing today, that's okay too. All right, we got one hand up. Quick testing. All right, just a few more minutes. I see we've got 2 hands up now. Just chug through that, and then we can discuss the results. Or I guess you can discuss the results with Mr. Dubik on Monday, um, because obviously it would be a little awkward to just sort of sit there and not talk about anything on Monday, and then we talk about it on Wednesday. Um, but yeah. Alrighty, we're at 8:50 now. We got 3 hands. All right, so we're just about everybody. Um, so I think come Monday, you guys will be able to discuss the results with Mr. Dubik, and hey, 4 hands. Um, be able to discuss the results with Mr. Dubik, go over, why exactly everything is the way it is, you know, why it is the way it is. Um, and then hopefully that will help elucidate some more things. But like I said, that's going to go ahead and do it for today. So what I'm going to do is I'm going to give you guys the poll questions, and then if you have any questions of your own after that, you're more than welcome to ask those of me. They can be related to the lesson or not, as always. But if you do not have any questions after we're done with the poll questions, you're more than welcome to head out and have a wonderful weekend. You're not going to have any lab this week. According to Mr. Dubik, and I will try and get the recordings of this class up tomorrow, um, so that you guys at least have that for Monday. So yeah, let's go ahead and get started with the poll questions, and then we can do question and answer time, and you guys can break for the weekend.